Hello everyone, welcome to 10-Minute Physiology. In today's video, we're going to see how photoreceptors respond to light and dark. So with that, let's give it a go. So in order to understand how photoreceptors respond to light and dark, we're going to do an experiment. And in this experiment, we're going to have a cone, and this cone is connected to a monitor. And this monitor is going to show the change in membrane potential that occurs throughout the course of the experiment. So we're going to start off this experiment by exposing the cone to complete darkness. And what we're going to do is we're going to measure the membrane potential of the cone in complete darkness. So then after this, we're going to expose the cone to flashes of light at varying intensities. And what we're going to do for each flash of light is we're going to see how the membrane potential changes in the cone for each flash of light for different intensities. So with that, let's begin the experiment. So we're starting off with the cone in complete darkness. And if you were to measure the membrane potential of the cone in complete darkness, what you would see is that the cone would have a membrane potential of negative 40 millivolts. And this happens to be the resting potential. Now, if we were to expose the cone to a flash of light, what would happen to the membrane potential? Well, first of all, we have to know what the intensity is of that flash of light. And we're going to model that intensity of the flash of light with this monitor here. So the first flash of light looks something like this. So what we have here is that we have a flash of light, and its intensity is going to be modeled by the height of this rectangle here. So we start off with darkness, and then we turn on the flash of light around here, and the intensity of the flash of light is going to correspond to the height of this rectangle. The higher or the taller the rectangle, the greater the intensity of light. So for the first flash of light at this intensity, we see a membrane potential response like this. So when we expose this cone cell to the flash of light, what we see is that the cone cell hyperpolarizes in response to the flash of light. So this hyperpolarization is caused by a flash of light. So what if we were to increase the flash of light's intensity? Well, if we were to do that, modeled by this yellow curve here, what we would see is a hyperpolarization looking something like this. So you should see from this flash of light two things. The first thing is that the hyperpolarization produced in the cone cell is greater than the first one. And the second one is that the duration of the hyperpolarization is also greater in this one than the first flash of light. So how would the cell respond to another flash of light with an even greater intensity? Well, when we do that, what we see is something like this. So we see that the degree of hyperpolarization increases and the duration of the hyperpolarization increases. So from this experiment, we see a few things. The first thing is that brief flashes of light cause hyperpolarization in photoreceptors. And the size of this hyperpolarization is going to be correlated to the intensity of the flash of light. However, after a certain point, the peak will saturate, and this means that after a certain point, the hyperpolarization degree will not change anymore. It'll reach a maximum value and it will stay there. The other main thing that we see from this experiment is that the hyperpolarization, the duration of the hyperpolarization, is going to be directly correlated to the light intensity. The greater the intensity of light, the greater the duration of the hyperpolarization. So in general, the main point that I want to get across to you is that when we expose the photoreceptors to light, they are going to hyperpolarize. But how does this hyperpolarization occur? Well, in order to answer this question, we're going to bring up a rod. And this rod is exposed to complete darkness. And what we're going to do is we're going to magnify the plasma membrane in a specific region of the outer segment. And when we magnify it, we see a specific channel, and this channel is an ion channel that is gated by cyclic GMP. So cyclic GMP, which is inside the rod cell, is going to be in great abundance in darkness. So when the rod cell is exposed to dark, the cyclic GMP levels are going to be increased, allowing cyclic GMP to bind to this channel. Now, when cyclic GMP binds to this channel, this causes the channel to open, which allows sodium to flow into the cell. Now, at the same time, we also have a potassium channel in the outer segment. And this potassium channel allows potassium to flow out of the cell. So this is going to complete the current. So you have positive charge in the form of sodium entering into the cell, and then the same amount of positive charge exiting the cell in the form of potassium. So this entering of sodium and leaving of potassium is going to be called the dark current. And the dark current is going to keep the cell in a depolarized state. And this is going to be responsible for helping to maintain the rod cell and cone cell at that relatively depolarized resting potential of negative 40 millivolts. And this dark current is going to be responsible for leading to a constant release of neurotransmitter. So it's in fact in the darkness when rod and cone cells are going to release the most amount of neurotransmitters. So what if we were to expose the rod cell to light? Well, if you expose the rod cell to light, the cyclic GMP levels inside the cell decrease. This causes this channel to close, which keeps sodium from entering into the cell. But even though sodium has stopped entering into the cell, potassium is still leaving the cell. This means that positive charge is leaving the cell, and this means that the cell is hyperpolarizing. So in response to light, the channel here closes, which keeps sodium from entering into the cell, but the potassium channel remains open, allowing potassium to keep exiting the cell. This means that the cell will hyperpolarize in the presence of light. And this is why photoreceptors hyperpolarize in response to light. So in summary, we talked about how the resting potential of photoreceptors is around negative 40 millivolts. We talked about how in the presence of light, the photoreceptor cells hyperpolarize, decreasing neurotransmitter release. We also talked about how as light intensity increases, the degree of hyperpolarization increases up until a saturation point, and the duration of the hyperpolarization increases. We also talked about the dark current and how it keeps the cell depolarized in the dark, allowing a steady release of neurotransmitter. And then we lastly talked about how light stops the dark current, causing a hyperpolarization. So I hope this video helped you understand these topics, and I hope to see you in the next one. Thank you for watching, and I hope to see you next time.